Следующую спикерку сегодняшней конференции это Тетяна Марtyniuk, ML Researcher. Также она занимается ресерчем в УКУ ML Lab, и она расскажет про Image Restoration with GANs. Таня, прошу. Аплодисменти, конечно.
Привіт, мене чути добре? Привіт всім. Мене звати Тетянка. Я, напевно, переключусь на англійську, щоб всім було зрозуміліше, бо мені дівчата казали, що в нас є гості з-за кордону. So, yeah, I'll be talking about image restoration with GANs. I've been working with image restoration for a while, both in academic research at UCU, and also I've been with a team of Let's Enhance for a while. We've been doing lots of stuff with image degradations. So yeah, let's start. That's short, like table of contents. So first we will start about what the problem itself is, what is the field of image restoration. Then we'll switch to GANs, like just to give you a short recap what it is. Then we'll switch to objective functions that we use when training GANs, to metrics and what are the problems with metrics when you training GANs and trying to evaluate them. Then I'll switch to deblurring GAN v2, which is our joint work with Orest Kupen and guys from Texas A&M University. We've been presenting it last week in Seoul, South Korea, at International Conference on Computer Vision. And then just a few more things about real-world setting. And yeah. So what are the image degradations and why are they important? Well, if you look at like keywords that are really popular at top-tier conferences, lately you'll probably not see much of low-level vision and image restoration. Like still, there are lots of object detection papers, lots on segmentation, 3D is on its rise, but low-level vision is more or less very niche field. But I would say it's really very important, and just to give you a short introduction how many different degradations might be. You can have motion blur here, you can have haze, like this milky veiling caused by fog or any other weather conditions. You can have different types of noise. You can have raindrops and you can have rain strikes, and there are lots of different methods. They really, like, these problems are really different and treated differently. You can have bad lighting, and there is a huge subfield just in trying to enhance images, like make brightness better, make contrast better, and just make the lighting better. Probably the most famous part of image restoration is super resolving low resolution images, and there are many others. So why would we need them? These image restoration techniques? Well, first of all, because it's not that we're doing research just for research, just to manage to restore bad images, right? But when we're solving other problems, we rely on rather good data. Like, we don't have many bad weather conditions on data sets that we train our algorithms on, so we would really need it as a pre-processing step, so to say, to prepare our data sets to be as good as possible for other tasks in our pipeline. And also, where we're talking about cameras, when you have surveillance systems and you have just outdoor settings and bad weather conditions and lots of rain, fog, etc., or just a bit blurry shots because of movement or something, that might be really a problem. Okay, so basically why it's a huge disaster for researchers, because it's rather ill-posed problem. So you don't really know the nature of degradation when you have bad image coming to you. You just know that it's probably some combination of noise and other artifacts. There might be lots of them. So apparently you don't really know what the mapping is. You have to guess it somehow. So it degraded image in some sort of, like, you lost some information and you're trying to restore it. And yeah, you may find lots of research that is formulated in such a manner that, like, you know the nature of noise, for example, already, and you're trying to resolve this problem. Well, it might be published, because academia sometimes it doesn't really deal with real-world problems. But what you really want to have in your real-world setting is trying to solve it, like, completely blindly, just not knowing the nature of degradation in advance. So there's lots of lost information, and we have to manage to hallucinate it somehow. And that's where the GANs come in your play. And what are GANs basically? Well, in general, you have two networks that are competing with each other. You have generator and discriminator, and they're playing like Minimax game, trying to fool each other. So generator, it gets, in classical setting, just noise vector, and it tries to generate something that we would like to be really very similar to real data. And discriminator tries to distinguish whether something the generator produced is real enough, so to say. So it knows what is real distribution, it sees what generator outputs, and it just tries to say like, no, you have to learn a bit more because your outputs are shitty, and you just have to learn more and more and more, do it better. They first appeared like in 2014 in Goodfellow's work, even though there are some people that claim that they were even before that, like Schmidt-Huber said that he invented the GANs framework in the 1990s, but no one knew about it back then. So anyway, we refer to classical GANs as to 2014 novelty. And what are the GANs that we're using in image restoration? Well, they are conditional GANs. Why so? Because if you think about image restoration problem in classical setting, when you have, for example, like paired data, degraded image and a target image, which is already good one, like restored one, you want to give the generator not just some random noise or something, but you want to give to it this degraded image and to have its output be conditioned on this degraded image, because you want the distortion to be as little as possible, but still restoring information that was caused by degradations. So conditional GANs means that you are conditioning on that input of degraded image that you got. Well, and probably the huge raise in GANs for image restoration was when Pix2Pix framework was introduced. So at CVPR in 2017, there was this group by Philip Asola et al. They're still working with GANs and producing lots of cool stuff. I'll show it later. So they showed that Pix2Pix, this conditional GAN for image restoration, it really works. It works in different settings. You may have like sketches to real-world images like bags or boots. You might have seen it already, like black and white color, labels to facades, so on and so forth. So what you do, you have like one domain, another domain, and you want to like produce from, for example, from the day image, the night one. So that was a huge blast. Like everyone started talking about it and trying to use this framework, Pix2Pix one, in their settings. But GANs, like the classical ones, they had really lots of problems with convergence, and they were really cool as work that lots of people tried to base their research later on it, but there were lots of problems. And Wasserstein GAN was one of the attempts to try to solve the problem of training GANs. So they said, okay, KL divergence or JS divergence that we're trying to minimize as train with subjective function is not really good. It's hard to train. What if we make it somehow more intuitional? So we want generator to replicate the distribution of real data and do it as good as possible. So if we have like fake distribution and real distribution, we may think about it like piles of ground, so to say, and we want to move that ground. That's why, like, move that pile of soil, whatever, like that's earth mover distance here, with minimal cost. And the minimal cost that you have to pay for moving that earth from fake to real distribution, that's basically like what you want to estimate. It was still not perfect. They had to deal somehow with the restrictions and assumptions that they put on their framework. So what was the restriction? The function had to be 1 Lipschitz, and they said like, okay, we'll just do weight clipping. So we'll just do it straightforward. It works. We know that it works really bad, like meaning the intuition behind this is rather like, okay, let's clip the weights and it just will be working, but we don't know how to deal with that. Now we encourage you to develop something new, but for now, like, we'll live with that. And later on, the GAN GP appeared, so to solve this weight clipping problem, they said, okay, we can overcome this issue, we'll just add the gradient penalty, and you'll you'll never need this Lipschitzness anymore. But the GANs GP are really hard to train, so there's always a trade-off. Like they're very slow to train, they're still hard to train, but you don't have this assumption anymore. Lately, there was even one more paper, like last week I saw it at ICCV 2019. They say that, okay, Earth mover distance is cool, but we have to make something even better. They usually use L1 transport cost for moving that Earth pile, but what if we do it in a quadratic manner? Because it actually, they even claim that it converges always at poster, but when you look in the paper, it's not always. You have lots of assumptions there, but still, if you want to just dig into the math there, you can check it out. I haven't tried it yet in practice, but they claim that it works, at least for image generation. What I found really great with another things that the improvements of objective function for GANs was a relativistic approach to dealing with GANs. So it's not just that you want the discriminator to know what is good, what is bad, like 0 for fake data, 1 for real data, and having like 0.5, so like random guess when everything converged, and it doesn't really distinguish anymore between fake and real. They rather say that, okay, it's rather, we would like to it to be really flexible, and when it learns, we would like to have the discriminator to exploit the information that real data is less real when it's training, like fake. When discriminator is training and you it starts to understand that fake data is fake and real data is real, it's really like to decrease the probability that you always obtain 1 for real data. So that's what you have here. In usual setting, you'll just have for fake data rising probability from 0 to 1 when it doesn't distinguish anymore. But what we really like to have is for them to meet somehow in between. So relativistic GANs, they really work, I would say, better, and in the deblurring GAN V2, we actually use this one. Okay, so still we have to estimate the distortion somehow. We can compare images like pixel-wise. So we have the output, we have the target image that we want to compare them. But pixel-wise losses, they usually tend to output blur results when you train with them. But if you have GAN objective, it might not be very similar to all of them, like trying to just average everything. But it will produce something kind of realistic. It might be different all the time because it's very stochastic, and it will just produce you better details because this blur, it will be overcome by GAN objective. But it's usually not enough, and you want to exploit something more. Like you still can add pixel-wise losses if you want to save your color consistency and other stuff, and just generic information about the intensities of pixels in your picture. And you can add GAN objective to have fine details, but you'd also like to have some semantic information, like what's going on in your image, and that's where perceptual losses come into play. So you don't just compare intensities of pixels now, but you rather have feature representations of your samples, and you try to compare them MSE-wise still, but features and not just raw pixels. And depending on how deep you go in these pretrained features of, usually it's VGG network, you can actually obtain different results, like capturing rather very rich semantical information or rather more sparse one. But perceptual loss, even though it was a huge blast as well, it also had problems. Like, for example, if you think about style transfer, which is also image-to-image translation problem, and you want to have this Van Gogh style, and you want to use this content image and to have something really realistically artistic produced, you might have something like this, and it looks rather plausible, right? But the sun circles that are in the sky only in Van Gogh picture, they're somehow all over the image, like here on canal, here on some houses. So it doesn't really understand that that was the sun there. It just does something that produces you, well, still good results semantically, but not that good. And that's where the Technion guys from Israel institution came with. So they said like, okay, let's start something even better than perceptual loss. Let's call it contextual loss. And what we'll do, it's not just we want to match features like MSE-wise, we want to capture the bijection between image features. So if you have these blue triangles here and red circles here, we want to really encourage them to be not just really close, but also to have this one-to-one correspondence between them. And only then you'll have, you'll know that the images are similar enough. Okay, so that's a really cool paper. They have two different ones. If you're really into that, you have to check those. Yeah, but there are lots of problems with GANs. Like, this very over-informative slide, I would say, with lots of text. But anyway, the problem with GANs is I would not claim that there are lots of people that can train them, right? So first of all, it takes time. It's really slow. It does not converge much. Like when you approach people with posters at these conferences and you just ask like, okay, but what about your losses? Like, did it converge somehow? And they're like, we trained it for like 300 epochs or 500 epochs. It just started reproducing somehow the real data distribution, and we were like, okay, we're done. But the convergence, no, it was not an issue. So yeah, and also you have like lots of times you have mode collapse. Like generator just, due to huge data variability, it just can't capture all the information that is hidden in this data distribution. It just starts to produce some modes, and it's good with that. And that's a huge problem, right? So you can do lots of stuff. Well, probably the easiest ones would be like for WeGAN and WeGAN-GP, actually you can balance the updates of generator and discriminator, because it's not really good when one outperforms other. Because when they start being like very good, like discriminator is very good and generator just still produces some random noise, it will never learn something good, because discriminator will all the time just punish it, punish, and it will not be able just to become better. Also, you can have like one-sided label smoothing, but you should do that only with positive labels. Why so? Because if you change like zeros for fake data to say 0.1, there is no need for fake data to try to become more realistic then, due to changes in your objective function. Well, you can also do like feature matching. That's what we already talked about. Like discriminator tries to learn something really important when trying distinguishing real and fake data, right? And through the course of learning that, discriminator is rather heavy network, sometimes it's really deep one. Like when you go in depth in the features that it has learned, probably it learned something really very important in distinguishing those, so it might be an option for better training to compare those features. And yeah, many others, like you can still use multiple GANs for your task. For example, if you have mode collapse and you just can't capture all the variability of your data, well, you can try to specifically train one GAN for, I don't know, generating dogs and one GAN for generating cats or something like that. But it's really exhaustive, like no one does that. But still, it's an option, right? Okay, now about the evaluation. Well, evaluation is really a hard issue here, because what is good restoration? What is good enough enhancement, right? We usually refer to it as like subjectively it looks good, but what is the good metric? Like it's not a classification task, right? It's not that easy. Well, usually if you dig into the papers on image restoration, you'll see PSNR and SSIM metrics. This is peak signal to noise ratio. This is structural similarity index. Well, people try to beat each other, like being state of the art in either this or that metrics, but still, like, it doesn't prove you anything. Like this one, you can really fit it, just train it with raw pixel MSE loss, and you'll be fine. Like you can have 33, 35 in, say, image deblurring, just trying to train on PSNR. 33, 35 is rather good result, by the way. But you'll never have like plausible results, meaning perceptually. If you show it to real users, they will never say like, this one is better than that one, because it will be just blurry and no one would care. So there is a huge problem in that, and if you look into lots of challenges that are usually held during these top tier conferences, like you have entire challenge at CVPR each year, you have PERM challenge once in 2 years at every ICCV, and there are many others, you'll see that they try to come up with some perceptual metrics that is neither PSNR nor ICCV. And the guys from Technion, the same guys that came up with contextual loss, they did a great paper on the trade-off between perception and distortion. Apparently, you they claim that it's impossible to have both. Still, it's not like real proof because they still restrict it to some sort of like you have to have specific type of algorithm, specific type of matrix, but it's rather reliable empirically. I mean, there are lots of different algorithms that lie either in this cluster or in that cluster, and for now, still we haven't managed to get somewhere here. That's an image super resolution, but apparently it works for lots of tasks as well. So there is a report on it, and there is exhaustive study of those metrics. And what they came up with, like for evaluating what is perceptually cool, they made an attempt to look at the correlations with subjective scores of the audience. And they realized that this linear combination of two metrics, like Nikui and one mice, probably his surname, like surname of author of the paper, you can look for the details here, it like correlates best possible what they found, so they're like, okay, let's go for it. But still there is room for improvement, like it's still not good enough. Yeah, so that's it, and now I'll switch to deblur GAN v2. Deblur GAN v2 is our work on single image blind motion deblurring. So deblurring is one of the major tasks in image restoration, and it is a lot different from deblur GAN, like vanilla version. There might be lots of you who, if you're into GANs, you've probably heard about deblur GAN. It had lots of problems. It still did not output realistic enough results and results of perceptually high quality. So we tried to change a lot. First of all, we tried to develop the framework that will be good enough for any image restoration task. Because basically the only information on deblurring that we give to our network is the data that we provide to it. Apparently you can feed not just blurry data like blurry image and target image, which is clean one. You can also do it with hazing, you can also do it with super resolution, just changing a few dimensions, spatial dimensions here, and with any other task. So this is generator, this is discriminator, and what's really cool about it, it's really very flexible. We understood that those approaches that are based on pix-to-pix frameworks, still trying to replicate like the success of those, they are either UNet-based or ResNet-like, the same that you have for deblur GAN, and it's not good enough. If you go into object detection field, you see that FPNs, feature pyramid networks, they work really cool there on capturing multi-scale stuff in your sample image, right? So we noticed that the deblur GAN vanilla version, it doesn't really capture different levels of blur, different levels of magnitude and blur, and just scales of those. So we realized that we want to deal with multi-scale features, but not in the way that deep deblur works. Deep deblur has just 3 separate branches of input image in different spatial resolution, and it's extremely heavy, it's extremely long inference time, so that's not what we want. So we just decided to put the FPN backbone here, and you can change any, you can choose any backbone, you can try to go for really sophisticated ones, and they'll produce really cool results. I'll show you on the next slide. Or you can opt for really lightweight ones, like you can have MobileNet v2 with some modifications, and you'll be able to run it on device, like real time. If you want to, for example, imitate real-world video deblurring, but do it frame by frame, not exploiting temporal information, but still, you can have really lightweight network, just plug in into playing with really lightweight backbones. Like, we even tried to change MobileNet v2 even more. We added depth-wise separable convolutions, and it became even lighter and even faster. So yeah, that's probably the main contribution. So now it started capturing different scale degradations. Also, we decided to capture both global and local information when we're trying to train our discriminators. So now we have like 2 of them. One works with patches, the other works with the whole image. Like this one, it corresponds to fine details. This one, it works really for better consistency of your image. Maybe for deblurring, that's not that much of an issue, but if you're working with something that really changes the intensities of pixels, like dehazing, then you'll probably really need this global discriminator, because otherwise you'll just have this patchified version of what generator is straight to output. Okay, so those are the results. Sure, you can't see the screen, but if you go and look in the paper, you'll see that the last three are our results, and these are subjective scores. So if you use really a heavy backbone, like Inception ResNet v2, or you can use SE ResNext or any other sophisticated one, you'll probably get really great results like this one. And what I said, like about the general image restoration pipeline, you can use it for any other task. I've tried to do it for multitask approach when I did my master thesis in UCU. So you can have blur, you can have haze, you can have rain. You fuse these features all together in the encoder part of your network. Then you have separate decoders. You can try to frame it in a different way, but still, like this one, it really worked. It benefits from the features you learn on different tasks of image different image degradations. It really benefits a lot from those feature presentations, and then it just outputs clean images for every task you give to it, and you have several discriminators. You can frame it in a different way, but it works if you plug in for this encoder-decoder part, this network. Yeah, so the code is available, by the way, so you can play with that. Everything is in the paper. Put stars on GitHub. Okay, now we're moving to synthetic data and why it's a problem. Like for deblur GAN v2, what we did was like, okay, our data that we trained deblur GAN with was not good enough. Like you can see ghost artifacts all the way, because what we basically do to obtain synthetic data for deblurring is like we take two consecutive frames, we just average them, and what you really get is like double-faced person with two noses, two foreheads, and other stuff. It's really bad. So we try to, as we train usually on video data, like frame by frame, like GoPro or DVD data sets, we realized that we can interpolate the frames, and we use video frame interpolation techniques. You can choose any, like you can have super slow-mo, you can have the ones with adaptive separable convolutions. It doesn't matter, it's just a technique that you use for creating your data set. And we averaged then the interpolated frames. We did it in a manner that, like, there were different factors of interpolation, so not to make it more robust and not to overfit to some specific type of interpolation. And it worked, but it's still not perfect, right? So it's still paired setting, we still have synthetic data, it's not good enough. If you go for synthetic data in other tasks, like if you look at denoising, I haven't found this picture on the internet, I'm sorry. That's from when I went at CVPR this year, and that's a photo of poster. So that's a great work of Google researchers, and they claim that if you use synthetic data for image denoising, like if you try to imitate the nature of noise, if you use like Poisson noise or Gaussian noise or any other salt and pepper noise, well, in your paper, you'll be a really cool guy. You'll beat state-of-the-art, like in PSNR and other stuff, but who needs that? Because when you switch to real data, back to real data, that's the best performing algorithm, and that's the year it was developed. It's 2008. Like, it's been more than 10 years, and it's still not good enough to overbeat it in denoising, in real data denoising. So do we really need this synthetic paired data setting? Well, I would say that not really, and these guys try to exploit what we can get if we switch to raw image domain, and that's really cool work to look into. So the basic idea is such one. You don't, when you're trying to develop your pipeline, you usually work with JPEG images, or already like, they have lots of compression artifacts, they are already in a really bad way to work with. They're usually like sRGB, but whatever, can be any other color space. But apparently the noise that is usually on your image, it's from the sensor of camera. So, and it is added to the picture not after it was already assembled in JPEG image, for example. It's added at the level even before demosaicing, the Bayer filters that you get from raw sensor data. So what they try to do, they take the sRGB image, they try to imitate the backward process of going back to raw pixel data. Then they denoise the image there, and then they go back. And I would say that that's the way to work with, one of the ways to work with any image restoration task, because when you're trying to synthesize data, you'll never be as good enough as the nature of the degradation itself. So you probably have to look in some other directions, like raw data might be an option for you then. And it's not even just about GANs, it's just about the whole field itself. It's really, it suffocates of having too much synthetic data, and the research is good for nothing, really. Also, you have the same with super resolution. So lately, there were added additional tracks to those challenges that they are really focused on real-world data there. Because what you get, I'll show you here. Probably you can't really see it. We'll share the slides, right? Yeah. Okay, great. So you'll see lots of squares here. That's just real photo that you feed into ESR GAN, which is state-of-the-art, probably in super resolution. It was first presented last year in Munich at ICCV at the workshop, so they won the perceptual quality track, and that's really bad output. And here it's the same, it's really bad output, but by ESR GAN. So when you train it on synthetic data, trying to make this, because the main problem with super resolution is that people think that it's very easy, right? You can just downsample the data, you get the training paired data, which is rather rare, I would say, to get it really easily, right? So you have high res, you have low res, and you just train with it. But then you'll just train for bicubic downsampling, and that's it. And when you go to real data, it's nothing like that anymore. So you have to try to find something new, and that's what the guys that won Real World Super Resolution Challenge last week proposed, that they are first working with. Like, they try to train their GAN in such a setting that they have high frequencies and low frequencies, and they train their GAN only here, like discriminator is plugged in just here, so you just train it for high frequency details, but all the rest is more or less like usual setting. It still has like this bicubic downsampling, but they claim that it really works in real data, and they tested it also. I haven't tried it yet still. There is no even paper yet, I believe. But that's the name of it. It will probably appear in the report of this challenge here. Okay, moving forward. So we have lack of real data. We still can try to obtain it. Like, we can try to model it as realistically as possible, but it will be really sensor specific. Like, if you're trying to model for some specific noise that you get from a specific type of camera, you can probably train for it and get the data, but it will be really sensor specific. It might be not an option for you. You can try to collect real data, and that's what Vladlen Koltun, he works for Intel Labs now. They have lots of works in image restoration as well. Lots of them are in raw sensor data, but still. If you've heard about learning to see in the dark, that's their work. And he said that his students just did enormous part of work. They just took their cameras and they spent lots of evenings capturing lots of photos, like in real world environment. But you not usually have lots of PhD students if you're working on some project, right? So it might be an option, but it's still really hard to get as well. Those were the problems with paired data setting. Well, you might try to work in unpaired data setting when you don't have this reference image, like low res and high res, or blurry and sharp, or hazy and clean. You can just have a collection of hazy images, a collection of clean images, and you want to try to imitate what would be the mapping between those two, right? So that's where cycle GANs go into play. You might work with them as well. So they really want to have this cycle consistency. If you go from one domain to another one, like from X to Y, you probably also want to have something like inverse mapping, so to say. So you want to go from Y to X backwards and still have intuitively close enough results, so it works for cycle consistency here. There have been some improvements, like this paper I liked a lot. It was presented last year at ICCV. So you don't have different latent spaces here. You have one latent space shared between those two collections, but you have disentangled different spaces that work for attributes of those two specific domains. Yeah, and also you can try to learn the degradation. Like, this was really cool paper as well. I really liked it, but it Spoiler alert, it doesn't usually work. It works just for faces. They trained it for faces, and they claim that it doesn't work for any other data because it's like there's too much variability there. So what they do, they don't really take it for granted that, okay, we can just sample the high-res images, get the low-res and train with them. They try to imitate what would the low-res images look like if they first train GAN in one direction, from high to low, on unpaired data setting, which is not aligned, but still those are faces. You take celeb A, you take some other data sets with human faces, and you train it in manner from high to low, and then after you learned how to imitate this low res, hopefully then you can obtain paired data and work in reverse order from low to high. It's really cool, but the authors say that, okay, we tried to do it not on faces, but on some real data. In general, it doesn't work. It just does not converge. But there's room for improvement. You might try. Yeah, and what I wanted to say, like the last thing, I would say that GANs probably are not on their peak anymore. So when they first appeared in 2014, there was a huge rise in image-to-image translation with GANs, starting with 2017 when Pix2Pix first appeared. But now I wouldn't say that there are that many papers with image restoration on image restoration with GANs. Because people realize that they've exploited lots of objective functions. You've seen them, BGAN, BGAN-GP, relativistic GAN, which can be added to any other GAN objective, just in a relativistic manner, and many, many others that I haven't mentioned yet. You can work with different architectures, but it's somehow already saturated, and people try to think about something more sophisticated. So there's you don't see that many papers nowadays on GANs, but still the best paper at ICCV was GAN-based. It's a lot different. It's trained on single image, that's why it's called SynGAN, and they do it on different patches of image and on different scales. You really have to check it. It's a really cool one. It can be used for different problems. Like, for example, that's for super resolution. And what you see here, like, these are two methods, the SRGAN and EDSR, GAN-based and not GAN-based, that work with huge collections of training data. And these ones are only trained on single image. And probably even from there, you can see that this one is sharp, a lot like sharper than these ones. They have it on paper, you can check as well. So it works really cool, and it works in different manner than what we really are used to, right? We don't have this huge collection of data anymore. It's still restricted to this single image. You have to retrain it for different tasks and like other routines, but that's the work that will probably be a foundation to huge raise in GAN field again, probably, hopefully. Maybe people will try to exploit some new things in GANs. And, well, funny thing is that the same guy, like, this guy works with Philip Isola, who first came up with Pix2Pix. They work in this lab together, and they had, like, almost the same GAN framework with single image and other stuff at the same ICCV, and those guys won best paper, and these guys didn't, and like, unlucky them. I just wanted to show you that there are lots of shared ideas in the community, and sometimes you come up with something that was already developed like a week ago or something. You have to deal with that. And that's the cool stuff they produce. They like have been trained only on this one image of fruits, and it really produces consistent results. So it doesn't just shrink image like how we are used to shrinking or something, or just making it larger or smaller. It really can produce lots of different results just based on those patches. And that's really cool. Yeah, so that's it.
Tanya, thank you very much for such an interesting topic. So guys, any questions? Applause, first of all? Yeah, sure. So, anyone? No questions? Okay. Thank you, Tanya, so much again.